Okay, so let me share my screen.
About the homework, I mean the assignment, if we take something from the generating functionology book, then also we need to give the reference.
Yeah, it's better to at least code the place from where you are picking up the
Okay.
result.
Okay.
That way it's easier for me to verify, it's easier for me also to check, and for you as well to see
Okay.
later what you did. Okay. Yeah,
And
so
each the assignments you said will be having 30% weightage, right?
I guess that's what I said.
Yeah. So, I mean, how many assignments do you plan to give, or how much is the individual? Is that planned or?
So that thing is not planned yet
Okay.
as
Okay.
such. What I have told you is that every 2 weeks we'll have an assignment, like
Okay. Okay.
every 8 to 10 days, sort of. And then I
Okay.
plan to keep some gap between, the deadline of the previous assignment and the release of new assignment, so that you have some time to breathe in between.
Okay.
So that way it will be like a fortnightly
Hmm.
thing. So we should have 5 to 6 assignments. But if your real question is how many marks are associated with the questions that I've given in assignment one, answer is don't worry about that. These
Okay.
assignments may add up to, let's say, even 200 marks, and then I'll
Okay.
scale it down.
Okay. Okay.
So ultimate thing will be to scale it down to whatever percentage I have promised.
Okay.
And then how much ever marks you get, it would be there.
Okay.
So out of 100, if you got 100, then out of 30, you get 30.
Okay.
Right? You do the math there.
Hmm.
Yeah.
So today
So
we will be doing the exponential generating function rules, like
that's
one.
right.
Yeah.
So I did not share my screen. Right? Yeah. So can you see my screen?
Yes. Yes.
Right. Okay. So today is lecture 6.
I'm feeling scared today because I am the only one who will have to answer all questions.
It's okay. This also means that you can be more interactive.
Yeah, that's
Okay. So today, what we're going to see, as we promised last time itself, that we'll see the analogous rules for the exponential generating functions. Okay. To recall, first of all, recall what were exponential generating functions?
they had that factorial thing. So it's like sigma of n greater than equal to 0 and a n x to the power n or f n x to the power n by n factorial.
So this is exponential generating function, EGF. Okay. As we've already told, this looks like an x raised to n, but along with this term. Yeah.
Yes.
So this is what we have already seen. And now in this regard, we want to see, so let's just see some notation. So for something like this, you say that fx is the exponential generating function that generates the sequence an. Okay,
Okay.
fine.
Yes.
Or sometimes you would just write f instead of fx as
Okay.
shorthand. Yeah. Now, as before, we will see. So, if sorry, if an is generated by f, then if you shift the subscript by 1, what will this be generated by? Sorry,
For an ordinary generating. Oh, okay.
EGF,
Okay.
exponential generating function.
Yeah. So the factorial, the factorial below will be multiplied by uh, 1 n plus 1 and uh,
So let us see this. So if you have this, now this is supposed to be the coefficient of x raised to n over n factorial, right?
yes,
So what happens here? Tell me. And on the other side, let's just, since it's always, we are just manipulating the things. Let's see. If you take a n plus 1 x raised to n, over n factorial, and you apply this operation on this, what this is?
n a n x to the power n minus 1 by n factorial.
By n factorial, right?
Yes,
Now, will this n cancel with this?
yes. Then n minus 1 we will be having n minus 1 factorial.
So you will have this over n minus 1 factorial.
Right.
Now, can you compare these two?
Yes, actually.
Yeah, so this
So they are
is
at the same.
equal to what? Yeah, I'm so sorry. Hmm. So the sequence an plus 1
So
is generated by what exponential generating function?
this a so it will be an x to the n minus 1 the coefficient of x to the power n will be a n.
Plus 1. If the coefficient of x raised to n minus 1 is an, you take a plus 1 in all these subscripts, and what you get, the coefficient of x raised to n upon n factorial will be an plus 1, right? This comes as one piece. Don't forget this.
Okay, x to the power n by n factorial. Yeah.
Or rather, this is the part of the definition for the exponential functions, exponential generating functions. Yes.
Yes.
So when you already see x raised to n minus 1 over n minus 1 factorial with an an, this an plus 1 is coefficient of this, and this would have been arrived through a derivative of the original generating function. So this is nothing but f prime. Just check for yourself. So in this itself, if you had a summation an xn over n factorial, the derivative of this would have been some, so this would have started with n greater than equal to 0, right? N greater than equal to 0, an n xn minus 1 over n, sorry,
Just a minute, ma'am.
n minus 1 factorial. And then instead of starting from 0 and making no sense of this, what we do is we take summation n greater than equal to 0 rather than 1, and
Hello. Yeah. Can you hear me, ma'am? I think there was some issue with my audio.
yeah,
Okay.
yeah. So if you take, where is my cursor? So if you start with an xn over n factorial, summation starting from 0 and take its derivative, you
Derivative.
get an
Eh,
xn minus 1 over n minus 1 factorial.
Yes.
And now summation running from n equal to 0 does not make sense, right? Because of
Right.
these.
Yes.
So it
It will
really
start
runs
from
from
1.
this, and you write an minus 1 over n minus 1
Factorial.
factorial. But then this is same as saying that I raise one script here
Yes. And
and
xn
here
by n factorial.
and here, and then this can be reduced back to 0.
Yes. Right.
Isn't this term same as this
Yes.
term,
Yes.
right?
Yes. Right.
So this is nothing but d of f.
Okay.
That is why we said that the an plus 1 sequence is generated by the exponential generating function given by f prime.
Okay.
Yeah.
Yes.
Along the same lines, very quickly, can we do this?
F double prime, I guess.
Yeah, because at least this we know
After
would be generated by d of
d of f.
f, right?
Yes.
And which is d square of f. Okay. So
Yes.
with this, we now have our first rule. So let's, if f is the exponential generating function for the sequence an, then an plus h, this is h,
E to the power h f.
d to the power h f for any positive natural number, any positive number.
Yes.
Okay.
Right.
So with this, maybe later at the end, we'll make a table with which will show the contrast of rules of with respect to the ordinary generating functions
Okay.
and the exponential generating functions. Okay.
Yes.
Yeah. So next thing was what we did last time.
For n to the power k am. So we multiplied it by
Yeah. So if an is the exponential generating function for the, I mean, if an is generated by the exponential generating function given by f, then what is this given by? Okay.
So if we
Try.
multiply by n, n factorial, one of the n from the n factorial gets cancelled and it becomes n minus 1 factorial.
Okay. And what is that?
Uh,
So as you have already guessed, if I start with this, n greater than or equal to 0, this is nothing but an xn over n minus 1 factorial.
yeah,
But I know that this and this have to match up.
yeah.
So what are we going to do?
We can, I mean, change the indices and start from, yeah,
Right? Sorry, why would I do this? It still would make sense. So now these things match up. Okay.
yes,
And then what I have to do, I have to bring it down. So what I say, I take this and then this can become this. And now n will start from 0. Does this entire thing make sense now?
yes.
And what is this? We know what is this.
Oh, this is the generate exponential. I mean, if you start, this will start from 1.
Is this right?
Yeah, yes, yes,
Okay. So this D is applied only on F.
yeah.
So in this, if I had given another product, what would you have done?
Uh, will it be x square d square f?
So at least this answer we now know is
X,
XDF. Now, exercise for you is to figure out this. Sorry, not EF3, EGM. Yeah, please find this.
can you scroll up a bit so that I can see the previous n1? Yeah. Ma'am, are you saying anything right now? You are muted.
Oops. Okay, done.
No, actually, so I took x square out and I got an x to the power n minus 2 by n minus 2 factorial, and that gives x. And if I change the indices, I'm getting x square times summation n greater than equal to 0, n plus 2x to the n by n factorial.
Yeah,
Uh,
so then you will not get it in a nice enough form. But if you remember the last time also we did some tricks that instead of trying to do it directly, what you do is that I know how NAN is dealt with, right?
yes,
So if
from
my BN is NAN, I know
oh,
BN is generated by what generating function?
uh, n
If AN
derivative
was,
of
let's say, generated by F, then BN is generated by,
uh, n if yeah x
right? We just
yeah
now computed.
yes
And then you are having NBN. So
right
then this will be generated by
uh,
X of
d yeah
D of XDF, right?
yes
So this is nothing but what we write as XD square of F,
yeah
correct?
right okay
So we then have the rule 2 prime for us, which says that if AN is the exponential generating function generated by F, then for any integer positive n raised to h a n is
xd
the
to
sequence, yeah,
xd to the power h times f
applied on f.
yes
Yeah, remember this as an operator, how it operates. Okay,
yes it I mean it takes the derivative and then multiplies by x and then again takes the
correct,
derivative
correct.
does
It's
that x
not
time
like you take x raised to h
no
once and
yes
then keep on differentiating h times.
yes
No, that
right
is not how the operator is being multiplied. Okay, so let's not call this as a rule, but let's just keep this as an observation. And now, just as we did last time, if let's say Pn is a polynomial in n, okay, and then this Pn is multiplied with an, what this will be generated by?
it will I think it will be p of uh, p of uh, xt operated on f
That's right.
because yeah
Because obviously, like
yes
summation just distributes over, and
yes
the
and
other
for the
powers are
product it
taken care
gets
of
x
in this rule.
yeah right
Okay, so this becomes the rule 2 prime.
okay
Okay,
yeah
so this is what we have. Now let's just see a small example, not directly using this rule particularly, but just to see the power of what we have really simplified using these exponential generating functions. So you remember the Fibonacci sequence?
yes
Consider the Fibonacci sequence. Okay.
Okay.
So this was given as Fn plus 2
Is equal to Fn plus Fn plus 1.
plus Fn. Okay.
Yeah.
So if, oh, maybe I should not use if here. Let's just, so this was given by An plus 2 is same as An plus 1 plus En, right? With
Yes.
some initial conditions. Let's not worry for the moment what the initial conditions are, but if we just look at this, what is, so suppose An is generated by the exponential generating function f, then above recurrence becomes, what does it become?
If you multiply it by x to the power n and divide by n factorial and then take the sum for all of the
Yes.
terms, yeah, then an plus 2 times x to the n by n factorial on the left
Okay.
by n, yes, this sum runs, okay, and yeah, an plus 1 similarly.
So what is this term that I'm writing right now?
The right last term is f.
Yeah, this one.
This one n plus 1. So what we did for the first one.
So this is f. This is d of f.
Yeah.
And
D
this
to
one is d square of
d
f.
square of f. Yeah.
So what we actually get is that f
F
double
double
prime.
prime equals oh nice.
Is this better to solve? Does this
Yeah,
involve
the
any partial
differential equation.
fractions?
No.
Okay.
Yes.
Linear second degree differential equation,
Yes.
ordinary differential equation.
Yes. Right.
Quite easy to prove.
Yes.
Solve this now. And see that so far we have not even like made use of the initial conditions.
Yeah, we will be using it to get the constants for the second order
Exactly.
difference.
Exactly. So with this, you already know what the solution looks like for this, right?
Uh,
Let's not go into this.
okay.
Just solve this second order linear differential equation, ordinary differential equation. Okay.
Yes.
So the benefit which I have got here is not just limited to uh, simplifying the calculations. Obviously, calculations are simplified because the
Yes.
partial fractions are not involved. But what is even better is that we have not even so far used the initial conditions, which means instead of the Fibonacci sequence, if I was given any other sequence which satisfies this recurrence relation, it
The
would
same
still,
differential equation would hold.
exactly. And
Yeah.
then to get the constants, you would use the different initial
Initial
conditions which would
condition.
be given.
Right. Right.
So in one shot, you're able to solve several
All
problems,
right.
and that too in a much faster way. Okay.
Yes.
So this is one powerful thing what we are getting through the ordinary, the exponential generating functions. So we have seen two rules. What was the third thing? Remember?
I can I check?
We can check here.
Yeah.
Yeah. So rule 3 was the product rule.
Yes.
Okay. So let's come back and do this. So suppose F generates an and G generates bn. Okay, I'm skipping these most of the times, I guess, but it's understood, right?
Yes, yes.
This with curly bracket means the sequence.
Yeah.
Okay, so this really means that f of x looks like an xn over n
In fact,
factorial,
yeah.
and g of x looks like,
En xn over in factorial.
now if you want to do fx gx, or rather question is what is this generated by?
Yeah.
So this is the question. So well, that's hardly anything where what we can do about it rather than sitting down and computing. So let's say I write this. Because I'm like sort of doing it the other way around.
Okay.
Okay, I am first trying to see what FG is.
Okay.
Yeah.
They're just the product of and
So this,
dr x to the r. Okay, s by s factorial.
okay.
Yes.
And when you take these products, this is nothing but ARPS x raised to r plus s
Yes. R factorial
over
is
s factorial r factorial, right?
yes.
Now,
Right.
I'm so sorry. Now, in this, if I really want to extract the coefficient of a fixed power of x, what comes into play?
We need to set r plus x to some constant like k or something.
Right.
Uh,
So that's what we do now.
okay.
So we are going to deal with the x raised to n, and then the element that I have here is going to look like, oh, sorry, I have
No.
already taken n
Yes.
out.
R plus s minus n.
This r plus s equals n, and then the entire summation.
Okay. Yes.
Is this right?
Yes.
And how is this related with this now?
Sorry. Which related to what? Uh,
So ultimately what we, so this is what my FG is.
yes. Yes. We go. The coefficient of x to the power n in fg is that thing within the parenthesis.
Yeah, so this you are, so if, so this is what we have actually got, that if an was generated by the exponential generating function f and g generated bn, then summation er bs over r factorial s factorial
Will
r
be
plus
generating
s equal to
f.
n.
Yes.
This was generated by the fg,
Yes.
but ordinary generating function.
So yeah, right,
This O is important here.
right.
But we want to find the relation for the exponential
Exponential.
generating function.
Then we need
Okay.
n factorial somehow.
Yeah. So do further manipulation and from here see what we get. Actually, this was supposed to be one of the exercises, but let me leave this as exercise. Like I will skip
Okay.
it and leave.
We can, if we write s as n minus r, I think
Sorry.
if we write s as n minus r in the,
Mm-hmm.
then we get, I mean, ar b n minus r divided by uh, r factorial n
Okay,
minus r
let's do
factorial.
that. So you're suggesting that
No,
we
I'm not sure it
rewrite
will work.
n greater than equal to 0, x raised to n, and inside this we write r from 0 to n,
Yes,
ar bn minus r over r
yes,
factorial n minus r factorial,
yeah,
right?
yes,
So this is nothing but my fg. Okay.
yes,
And remember the rule which we had, a rule or rather notation which we had fixed in one of the initial lectures, that this
yes. The coefficient of in the
yeah,
formal passing, right?
this was the coefficient of x raised to
Yes,
n in fx.
right.
Okay. So the coefficient of x raised to n is this. So
Yeah,
coefficient of x raised to n over n
n
factorial
factorial
would be
multiplied by n factorial.
multiplied by n factorial.
Then we get the binomial NCR thing, I guess.
That's correct. In fg is equals to, or rather, let's just so in this you also do n factorial and n factorial here. Yeah.
Yes,
And this summation inside is independent of n factorial.
yes.
So instead of doing this here, I will actually take this inside.
Okay, yeah,
Okay.
yes.
So now n
Then
factorial
yeah,
divided by r factorial n minus r factorial takes the form of
binomial coefficient
binomial
NCR.
coefficient. So this is n choose r,
Yes,
ar b n minus r, and r ranging from 0 to
0 to n.
n.
Yeah, so this is the exponential generating function.
Yeah. So we we have the rule that we were looking for. If f generates en, G generates Bn, then An Bn is generated by
Summation R from 0 to n.
and
Yeah.
choose
A R B n minus R.
summation from R to N. Okay,
Yes.
is this right? This, so this is the
E.g.
this is the sequence which gets generated, right?
Yes.
These are the coefficient of x raised to n over n factorial,
Yes.
and this appeared in the product fg. We have simply manipulated here by multiplying and dividing by n factorial, right?
Yes.
So fg is the exponential generating function which generates the sequence whose coefficients are these
Yes.
from 0 to infinity. Okay.
Yes.
Okay. Now, after we have done this, what more can we see? So, okay, maybe let me share my other screen.
Okay.
Okay, can you see my screen?
Yes. Yes. Yes.
So what we have derived just now is this
Yes.
result,
Yes. Yeah.
that
Right.
f is the exponential generating function for a and g is the exponential generating function for b, and then fg generates this particular sequence. Okay, and
Yes.
remember that if we compare it with the result for the ordinary generating functions, the fg generated this particular sequence, right? We
Yes.
simply
Right.
got the
Last.
Cauchy's sum.
Yes. Yes.
And after this, so this really tells us that convolution of sequences is shown in this. There, like, whereas when you do the exponential generating functions, this actually takes care of the relabeling of structures also. So this is like almost always a good technique, that whenever you're trying to understand a big space or a structure, like the space could be a topological space, could be a ring, could be anything, and structure could be any of these which you can physically, sort of realize. So in such things, what happens is that sometimes it is not so easy to look at it as a whole. In such cases, we try to understand parts and parts of it, and then we try to put them together and see it as a whole, to what really happens to the entire picture if I know what happens on the small pieces of the pictures.
Okay. What did you mean by relabeling the structures?
So initially, if let's say you came with your name and then I came with my name, and then when we were to be put together, maybe our names did not really matter, or it mattered.
Okay.
So if let's say some n people came into the picture and we wanted to understand which are people we would choose out of these to make our picture,
Okay.
then there are ways to choose such people, right?
Yes.
But I have some R spots fixed. So then you appearing as Ridiman is not so important. But
Okay.
you appearing as, let's say, person one and me
Okay.
appearing as person two becomes more relevant.
Okay. Okay.
Whereas here I was fixing how you appear. Like if you are Ridiman, you are Ridiman. If I'm Shuchita, I'm Shuchita.
Okay.
But here I am in some sense losing my identity and I am just becoming one of the R elements which are selected.
But that AR, BN minus R term is still there, right? So, uh,
Yeah, so this just becomes person one, person two,
okay. Okay.
rather than Ridiman or Shituta.
Okay. Right.
Because now I am being led by this particular identity.
Okay.
Okay.
Yeah.
So then, like as I already told you, we are really what we are doing is that we are choosing the new levels of these elements, and we say that okay, of course, if you choose R elements out of a set of n elements, you have n choose R many ways to do this,
Yes.
right? And
Yes.
then AR many ways to choose
The
that
fast one.
structure,
Yes.
and
And
Bn minus R many ways to choose the
second
other
structure.
structure.
Yeah.
Therefore, this, like, although this is all very much becomes abstract, but this is the juice of it.
Okay.
After this, they have a I mean, you remember we did the bell numbers
Yes.
earlier,
Yes.
and
Yes.
this is part of your exercise also to
Yes.
figure out the exponential
Right.
generating function for the bell numbers.
Yes.
So here it's been done using what we have just studied.
Okay.
So this you can read on your own. I will not go
Okay.
into this.
Okay.
And this is the example which is nice. So let me just give a little insight of this particular example and then
Okay.
we will stop today's lecture.
Okay.
Okay. So you are already a computer science student, right?
Yes. Yeah.
So you understand all these legal
Yeah. Parenthesis. Right.
strings.
Yeah.
Yeah. So parentheses can be put, but not always in a fashion which makes
Yes.
it legal.
Yes. Yes. Yes.
Correct? Will this right here? No, it doesn't. There is a way to write. Huh? Oh, okay. I can't write on this piece, I believe. Not possible. Okay, let it be. So let's come down to the, okay, where I can write. So legal string of,
I can't see if you are writing anything.
oh, sorry. I did not change my share screen.
Oh,
Is this
yeah.
visible?
Yes. Yes. Yes.
Okay. So as our intuition says that if you have, first of all, parentheses are nothing but brackets,
Yes. Yes.
right? So what we're dealing with are these two kind of objects.
Yes.
Okay, this and this. Okay, these are the two things that we're dealing with. So something like this is called an opening bracket, or you sometimes also call it a left parenthesis, right?
Yes.
whereas
closing bracket or like
this is a closing bracket, or sometimes also called a
right.
right parenthesis. So if you do a parenthesis like this, is this legal
Yes.
or not legal? Yeah, this one is legal.
Yes.
If you do this,
No, not legal.
this is not legal. First of all, whenever you're dealing with these, the number of closing brackets and number of opening brackets have to be same,
Equal. Yeah.
equal. So
Yes.
is this a
No,
legal?
not no.
No. Is this legal?
No.
No. Is this legal?
Yes.
Yes. Is this legal?
No.
No. For everyone, you know the reason, right?
Yes.
This is legal because you are seeing the opening one first and then closing
We
one
can't
second.
see more closing parentheses before. I mean, if we keep track of both from left to right, there can't come a time when we have encountered more closed parentheses than open parentheses.
That's right. And the number of opening and closing
Yeah,
parentheses should be equal.
equal. Yeah,
Okay, so that is what defines a legal string of parentheses.
right.
Okay, so can you find, so if let's say I give you a string or so so okay, with the 5 brackets, or let's say 3 brackets, can you give me legal strings?
You mean a total of three brackets or only
Can
left?
you have a total of 3 brackets?
No, we can't have that. It
Yeah,
should be an even number.
or maybe let's just keep 2. Even 3 would be too much. Yeah,
Yeah, we can have one. Yeah, this one.
right?
And yeah,
This is also legal.
yes.
Is there any other way to,
No, these are the only two.
so let's say Fn be the number of legal strings with 2 in parentheses. Okay, so this means n closing
Yeah,
and n opening. Yeah,
right.
so what is this number?
I think we can use a recurrence to solve it.
Yeah, that is very hard to guess since we are in this course.
Yes.
So what kind of recurrence do you guess would work here?
I mean, if we know Fn, I mean, if we know Fn minus 2,
Mhm.
then we can construct I mean, yeah, if we have a string with n minus 2, total of twice n minus 2 parentheses, that is n minus 1 closing and n minus 1 opening, then we can construct legal strings of 2n parentheses by I, how many ways? Maybe by we can add an opening and closing bracket.
In
And
how many ways?
yeah, that's what I'm trying to work out. Uh,
Okay, since just 15 minutes are left for the lecture, let's see what I have in store.
okay.
So suppose what is here itself? K is the number of brackets. So now onwards, whenever I say, maybe I should have said 2 pairs of brackets.
Okay.
Okay. So then number of
Yeah.
pair of brackets that have been scanned while moving from left to encounter a legal string. Smallest such number. Okay. So what am I really saying is that if you have something like this, let's say, you start scanning from here. So you scan this, you scan this. So after you have scanned this is one number of pair. Is this a
Yeah.
legal string?
No.
Just this piece?
No.
No. So you go ahead and scan two more.
Yeah, we got a legal.
This is a legal string? Yes.
Yes.
How many pairs have you scanned to
2.
this? 2. So this has k equals 2.
Okay. Okay.
Okay.
Yes.
So of course, if I scan 5 and 6 also,
Then
again I
also,
will be
yes.
left with a legal string. But
Got it.
I want to scan the least number of pairs possible.
Okay.
Okay. So in this, so this has k equals 2, whereas this has k equals
1.
1.
Yes.
Now another thing we observe, after k pairs have been examined, left out portion in the string, is this legal?
After KPS, yes, that should also be legal.
Why? Because the entire string was legal.
Yes.
And you have just taken off
A
equal
legal
number of
something. Yes.
opening and closing brackets away from it.
Yes.
Right? And since you have done it from a corner, it works.
Yes.
It may not work if you do from in between, right?
Yeah, right. Right.
Yeah. So this works.
No, I think if we take out a legal string, string from the between, then also it will.
Yeah,
work.
from in between legal string. But
Yes.
if you have just taken off a pair, it may
No,
not.
no. Yeah, right.
So, and what you took out is again a legal string. So
Yes.
what really happens is when you had these 2n brackets, Okay, you scanned some 2k brackets. What is left is 2n minus 2k brackets.
Yes.
From a legal string of 2n brackets, we scan 2k brackets. Okay.
Yes.
So this k, remember, given any particular legal string of 2n brackets, this k is fixed,
Yes.
right?
Right.
And then once this k is fixed for that particular string, this string is also fixed,
Yes.
right? So the string, remember this function which we defined here, fn, is a number of legal strings with 2n parentheses. So all the parentheses with n pairs of brackets can be broken up as these k legal parentheses,
Yes.
and whatever is left is again a legal parenthesis
Yes.
with
Right.
n minus k many brackets,
Yes.
right? So here, this is a
Product of.
product. And what
Yes.
we did, what was the rule 3?
Uh, I
The
mean,
product.
this was for exponential generating function, but yeah, okay, yeah, this is the rule.
Yeah, so aim is to find out, or rather solve,
This recurrence.
this reconciliation. So now solve this reconciliation using the rules that we have studied. Okay.
Yes.
So yeah, I will not pick up a new thing now. Just 5 minutes left. You have any doubts?
No, no.
Of course, you will have to do a lot of manipulation even here. Okay,
So,
just write.
I mean, how will we multiply x to the power n and divided by n factorial in both sides and take a summation like
that
collation?
that is what you have to figure out. So if let's say you choose the generating function to give the sequence fn to be some g, then to
Okay.
obtain the left hand side as g, you will have to do the x raised to n over
Yes.
n factorial.
Yes. Yes.
Here also x raised to n over n factorial would be there, but then if you want to really use the product thing here, you will have to work with this k and n minus k further and
Right.
bring them to the form so that you can use this product rule which we
Yes.
studied.
Right.
Okay,
Okay.
so you will have a function which will be defined in terms of the same function but with the different subscripts.
Okay.
Okay, but that's all about the manipulation which we have to do all the time, right?
Okay.
We are in this course of counting.
Hmm.
So this here also we are doing the counting business,
Yes.
counting the number of ways you can draw a legal string.
Hmm.
Yeah.
Yes.
Yeah, any other thing?
No.
Okay, so let me stop this here.
Uh, so we won't be meeting next week, right?
Yeah, there is no lecture in the next week.
Okay.
However, your assignment is due
Yes.
Monday night.
Yes. Yes.
Okay, so you have to upload it on the Moodle. Like if you don't
Yes.
do it by Monday night, it will not accept your
Yes.
submissions. Okay.
Okay.
and the